Okay, everyone, let's begin then. So we were doing integration. In the last couple of classes, we've talked about integration by parts, right? How to integrate products. That's what we've done in the last couple of classes. We've basically covered pretty much everything that we need to know about that. Now today, we want to start with the last major part of this topic, and that is integration by substitution. All right, so that's the plan for this particular session. We will cover integration by substitution. And along with that, we want to basically understand how to integrate powers of sine, cos, and tan, power 3, power 4, power 2. How do you integrate all of those functions? That's the plan for today. Okay. And then after today, we should be done with all the topics, all the concepts that we need to know about in integration. So you should be able to complete the worksheet after today. So our next class is on Friday. So before Friday, I would expect that you would have attempted most of the questions from the worksheet so that you know where you're having problems. And we could then discuss some of those problems in our Friday class, inshallah. Then on Saturday, we could perhaps start differential equations. That's not a very big topic in terms of concepts, at least. So that's not going to take much time. So we would want to cover that this week as well in terms of concepts. Then you'll have some time to practice, and we could discuss the problems that you have next week, inshallah. But for now, let's start with this integration by substitutions. Now, integration by substitution, although its method its working is sometimes slightly confusing, slightly complicated, but it's straightforward in the sense that at least you do not really have to think about this a lot, in the sense that they will always tell you that you have to use a substitution when you are required to use it. All right. So in the other types of functions and the other methods of integration, for example, all of these methods that we learned about, how to integrate, when we have to integrate by parts, when you have a product and you have to integrate by parts, and when you have all of these other forms, ln rule, tan inverse rule, partial fractions, splitting the numerator, improper fractions, and so on, all of these, you have to basically figure it out yourself by looking at the question, looking at the function, that, okay, which method is going to work on which function. Substitution, in that sense, is relatively straightforward, that they will always tell you that you have to use a substitution when you are required to use it. And they'll also tell you what substitution to use. All right. So you will be exactly told what to do in substitution questions. So that makes it relatively easier in that sense, at least figuring out what exactly you've got to do. Now, let's see how this is going to work. So let's start with an example that we did in our last class. For example, in the last class, we integrated this function sine x into cos x using integration by parts. We learned how to do it by making a loop like this, right? Where the same integral comes again when you apply integration by parts. But you could actually do the same thing using substitution as well. But if you were required to use substitution, they will tell you in the question that you have to use substitution. So let's take an example. Let's say they ask you to use this substitution. Use the substitution u equals sine x to integrate sine x into cos x with respect to x. All right. So you need to integrate this function now, sine x into cos x, using substitution. And what's the substitution? The substitution is u equals sine x. So they have told you what substitution to use. It's u equals sine x. Now, how is the substitution process going to work? This is the substitution that we're given, u equals sine of x. So what you're going to do is you're going to replace sine x in this integral with u. All right. Let's see what happens when we do that. If we replace sine x with u, what are we left with? We have u into cos of x dx. But the problem is, this is actually even more complicated than before, because now we've got two different variables. We have u and we have x here. The idea is we want to convert everything in terms of the other variable, everything to the other variable. So initially we have everything in terms of x. When we use the substitution u equals sine x, the idea is to convert every single x variable in this integral to u. All right. And when that happens, this dx is also supposed to convert to du instead. Because when you have all the variables, all the expressions in terms of u, the integration will also need to be in terms of u. So you also want to convert dx into du. All right, dx also needs to be converted to du. Now for that, whenever you have to do substitution, along with using the substitution that they've given, u equals sine x, you have to do one more thing. And that is you have to differentiate the substitution that they've given. So it's u equals sine x. What you're going to do is you're going to find du over dx. So if u equals sine x, what's the derivative of u with respect to x? Du over dx. The derivative of sine is cos, so it becomes cos of x. And now since we want to change this dx to du as well, because we want to integrate in terms of u now, once we have converted everything to in terms of u, you want to make dx the subject in this derivative. So this is du over dx. Du over dx is equal to cos of x. What you want to do is you want to make dx the subject. How will that work? Dx, if you take it to the other side, cos x will come here, and we can say dx equals du over cos x. In every single substitution that you do, you're going to start like this. You will have the substitution given, you will differentiate it. After differentiating, you will make this thing the subject, whatever is here in the original integral. This is dx, you want to make dx the subject after differentiating. And that gives you dx equals du over cos x. And now what you do is, not only are you going to replace sine x with u, you're also going to replace dx with this whole thing. That's du over cos x. Leave everything else as it is for now. Just change these two things. Use the substitution given and put this thing, leave everything else in the function as it is in the first step. The first step, leave it as it is and see what happens. So in this case, we have u into cos of x. So that remains as it is for now. And we replace dx with du over cos of x. Now in this particular example, what happens is cos x and cos x get cancelled, and we are just left with integral of u with respect to u. And that is something that we can integrate directly. What's the integration of u with respect to u? We can just use power rule here, just like integral of x with respect to x. What's that? That's x squared over 2. Add 1 to the power, divide by the new power. It's just u instead of x. So this becomes u squared over 2 when integrated. And now you put that substitution back. You had assumed that u equals sine of x. Now put that substitution back and you say the integral turns out to be sine square x over 2 plus c. That's the integration of sine x cos x. This is how the substitution process works. Okay, now this was a very straightforward example in which a substitution was given and we just differentiated it. When we made dx the subject, the other x terms, they got cancelled automatically, right? In this case, cos x got eliminated itself. Sometimes you have to do something else to eliminate any remaining x variables. We will see how to figure that out. But this is how the process is going to work. Okay. I hope that makes sense. Now, let's quickly have a look at one more example in which we try to make it slightly more complicated. Okay. So now let's say we have to integrate 4x e raised to the power x squared plus 2. We want to integrate this function with respect to x. And you are given a substitution. Remember, in substitution questions, the question will always tell you what substitution to use. So let's say they have given you that you should use this substitution, u equals x squared plus 2. Now, given this substitution, how do we use it here? Let's differentiate it. That's the first thing you're always going to do given a substitution. If u equals x squared over x squared plus 2, what's the derivative of u with respect to x? It's 2x. And now you have to make dx the subject, and that gives you dx equals du over 2x. And you just have to input these two things down. Instead of x squared plus 2, you're going to put u. And instead of dx, you're going to input du over 2x. Let's do that and see what happens. We're going to replace x squared plus 2 with u. Let's do that. Leave everything else as it is. You're just going to replace these two things. Okay? We're not going to touch anything else in the first step that we do. Leave everything else as it is, and then see what happens. You have 4x as it is. E raised to the power x squared plus 2. X squared plus 2 gets converted to u. What about dx? Instead of dx, you write du over 2x. All right. And now you see if some cancellation happens. So in this case, 2x and 4x, they get cancelled. You're left with 2 here. And this simplifies to 2e raised to the power u with respect to u. That's a simple integral that you get. Now, this is something that you can directly integrate, right? What's the integration of e raised to the power u? Now, 2 is a constant that's multiplying, that remains as it is. What's the integration of e power u? Integration of e power u is just e power u. And that's your result. Now, put that substitution back. U was x squared plus 2. And you said this becomes 2e raised to the power x squared plus 2 plus c. That is the final integral that you get from this. Okay. So this is how integration by substitution works. Now,
Sir?
let me get, yes.
Sir, won't we even divide by u while integrating?
Remember, this is e power something. We're not using power rule here. So power rule is used when the variable is the base and you have some number as the power. So let's say x raised to the power 4. Integration of this is x raised to the power 5 over 5. If you have e raised to the power 2x, let's say, what's the integration of this? E raised to the power 2x divided by 2, which is the derivative of the power. Now, in this case, we just have e raised to the power u. Variable is u. What's the integration of e power u? Integration of e power u is just e power u divided by the derivative of u with respect to u. What's that? That's just 1. So e raised to the power u over 1. Just like integration of e power x is e power x, when we do integration with respect to x, here the variable is u instead of x. So when we integrate e raised to the power u with respect to u, the result is just e raised to the power u. Does that make sense?
Yes, sir.
So we're not going to use power rule here. This is an exponential function where variable is in the power. This is how we integrate it. So that's your final result. Okay. Let's take another example. Let's say now you have something like this. You've got integral of 4x into square root of 2x plus 1, and you want to integrate this with respect to x. And the substitution that you're given this time is u equals 2x plus 1. Now think about this, all of these examples, you cannot integrate them using the other methods that you've done. For example, this is a product. This cannot be integrated using integration by parts. That is why we have to use a substitution here. Similarly, in this case, this product, this cannot be integrated using integration by parts. You can try that, you'll get stuck because it will not be simplifying That is why in the question they've given you this substitution, because using this substitution makes this a simpler function that you can integrate after using the substitution. Okay, so this is the substitution that we're given, u equals 2x plus 1. Now, what's the first thing we do with that? We differentiate it. When we differentiate it, that gives us du over dx. What's the derivative of u with respect to x? Derivative of 2x plus 1, that's just 2. Now you make dx the subject because we want to get rid of this dx as well. And that gives us dx equals du over 2. All right. Now, let's just put these substitutions here. Instead of 2x, we're going to put u. And instead of dx, we are going to input du over 2. Okay, let's try that and see what happens. This gives us 4 into x as it is. So everything else, you're going to keep as it is. You're not going to change anything else. Inside the square root, you've got u now. And instead of dx, you have du over 2. All right. So you've replaced dx with du and 2x plus 1 with u. But now we've got a problem. And the problem is we still have an x here. In the previous examples, x was getting cancelled automatically. But it's not getting cancelled here. We still have this x. How do we get rid of this x now? Because we want the whole function to be in terms of u. We don't want any x terms here, right? So how do we get rid of this x now?
So we can make x the subject in
we can make x the subject in this substitution. So we have u equals 2x plus 1. We could write this as x equal to u minus 1 over 2. And that is what we could input in place of x here. And that will convert this x to u as well. All right. And then we can integrate it, because as of now, we can't do any integration because we have to integrate with respect to u, and we have an x here. So integration is not possible. We have to convert that to u as well. Okay, now let's try that. Now this 2 and this 4, they get cancelled. We have 2 left here. And then we can say integral of 2. In place of x, we can input this u minus 1 over 2 into square root of u into du. And now 2 and 2 get cancelled as well. And this is what we are left with, integral of u minus 1 into u raised to power 1 over 2 du. And now we've got everything converted to u now. How do we integrate this? How do we integrate this with respect to u?
We can simplify first.
We can simplify this. So one idea that might come to your mind at first would be that it's a product. So you could use integration by parts. You could try that. In this case, that can work. But it's much simpler to just simplify this. Just multiply u raised to power 1 over 2 inside. What does that give you? U into u raised to power 1 over 2. That's u raised to power 3 over 2. Minus 1 into u raised to power 1 over 2. That's u raised to power 1 over 2 du. That is what we are left with. And now we can integrate each of these terms separately. And that gives us u raised to power 5 over 2. Because remember, this is a power function. We can use power rule here. We have a linear expression and a power, and we have a power on top of that. So we add 1 to the power, divide by the new power. Similarly here, add 1 to the power, 1 over 2 plus 1, that becomes 3 over 2. Divide by that new power. And that's your integral. You can simplify this now. That gives you 2u raised to power 5 over 2 divided by 5 minus 2u raised to power 3 over 2 divided by 3. And that's your integral. You've integrated this. Now, if you wanted an expression in terms of x, you can put this substitution back. U equals 2x plus 1. What does that give you? That gives you 2 into 2x plus 1 whole raised to power 5 over 2 divided by 5 minus 2 into 2x plus 1 whole raised to power 3 over 2 divided by 3 plus c, and that is the integral that we were looking for. Is that okay? Any issues with this? Okay, good. So that's how substitution works. All right, this is how the substitution process works. Whatever substitution you are given, you're going to differentiate that, make dx the subject, if that's what we have here, and put those two substitutions there. All right, then integrate. Once everything is converted to u, and after integrating, you just put that substituted variable back in that function. Now, what happens is sometimes you get limits as well. So you might have some limits on the integral as well. For example, if the limits were from, let's say in this case, limits were 1 to 4, let's say these were the limits from 1 to 4. And you had to evaluate this integral with limits. Now, how would you do that? One possibility could be that after you've integrated everything, at the end, you input limits here. After converting back to x, you input those same limits 1 to 4. But often what we do instead is, we don't do this conversion and we just input limits in this function here. But since the limits originally are supposed to be values of x, if we want to input them in place of u here, we first have to convert those limits to something in terms of u as well. All right. Now, let's understand how to do that process using an example. So I'm going to do another example. Let's take an example from the worksheet. From that worksheet, we will look at a question in which you have limits and you have to integrate that by substitution. Let me see if I can find the worksheet here. P3 integration. Okay, let's have a look at one question in which you have to use integration by substitution, and there's some limits here. Let's have a look at this. Question number 4 from the worksheet. Now, it's a good practice question on substitution as well, and it'll also help us understand what to do with limits. Okay, so question number 4 from the worksheet. Let's have a look at this. Okay, so it says, use the substitution x equals tan theta to show that this integral can be written as this. So you have an integral that is in terms of x. You want to convert that to an integral in terms of theta instead. All right, using this substitution x equals tan theta. Now, let's see how this process is going to work. So what's the integral that we are starting with? 1 minus x squared divided by 1 plus x squared whole squared. And this is to be integrated with respect to x. Now, if you look at this integral, this is something that we do not really know how to integrate directly. It does not fall into any of those standard forms that we have discussed. It follows none of those rules. That is why they have given us this substitution that can help us integrate this function. Now, what's the substitution given? The substitution given is x equals tan theta, right? This is the substitution that they've given us. Now, how do we start with the substitution process? The first step that we always have to do is we have to differentiate it. Let's find the derivative of x. Now, the variable on the right side is theta. So when we differentiate it, it's going to be dx over d theta. What's the derivative of tan with respect to theta? Its derivative of tan is secant square. So dx over d theta, that becomes secant square theta. So now x is supposed to be replaced with tan theta. And we also need to get rid of this dx from here. So we have to make dx the subject. When we make dx the subject, that gives us dx equals secant square theta into d theta. That's the other thing that you have to input in that integral. Okay? These are two things that you need to input in that integral. Now, let's do that. So wherever you've got x, you're going to replace that with tan theta. So this becomes 1 minus tan square theta divided by 1 plus, this is x squared. So this becomes 1 plus tan square theta. And there's a whole square on top of that. And what about dx? Dx is going to be converted to secant square theta into d theta. So this becomes secant square theta into d theta. So everything is converted to the variable theta now, right? All the x terms are gone and everything is in terms of theta now. Now we need to convert it to the form that is given in the question. What's that form? They want us to convert this to cos of 2 theta. So after this point, we are actually done with the substitution part. Now it's basically trigonometry. You have to use some trigonometric identities to go from this form to this form, right? That's the problem now. You have to go from this form that is in terms of tan and secant and convert it to cos of 2 theta. Now, how can we do that? Let's try to figure this out. How we can go from this form to that form. Okay, now, first of all, you should notice the angle that we have here in the form that we have, that is theta. That's a single angle. However, that the angle that they have in the form that they want, in that form, the angle is 2 theta. So you have to use the double angle identity here. What double angle identity? The double angle identity for cos. So you should have the forms in front of you. You should have the formula sheet in front of you. What is cos 2 theta equal to? Cos 2 theta is equal to cos square theta minus sin square theta. Or you have another form which is 2 cos square theta minus 1. Or you have another form which is 1 minus 2 sin square theta. So you basically want to convert this integral to one of these three forms on the right side. Once you have any one of those two forms, one of those three forms, you can convert that to cos 2 theta, right? So that's what we want to get to at the end from this integral. Now let's try to simplify this a bit first. How can we simplify this? So we have two functions here. One is tan and the other is secant. What's the connection between tan and secant? Does anyone remember that? Tan and secant, how are they connected? Do we have any identity connecting tan and secant? We have 1 plus tan square theta, that is identical to secant square theta. So that can be used to maybe get rid of one of the functions here. If you notice in the denominator, you have 1 plus tan square theta. So using that identity, you could actually simplify this a bit and write it like this: 1 minus tan square theta divided by secant square theta whole squared, and we have secant square theta here as well, into d theta. Now secant square theta, and in the denominator, we've got secant raised to the power 4 theta. They kind of get cancelled. And you have 1 power of secant. We have only secant square theta left from that. And we end up with 1 minus tan square theta divided by secant square theta, d theta, right? So this secant square theta gets cancelled with 1 power here, with power 2. And you're left with just secant square theta. Okay, now this is slightly simpler than before. What do you want next? Keep the end in mind. What do you want at the end? You want one of these three forms, okay, in order to get cos of 2 theta. How can you get to that form? you want something in terms of cos and sine, right? That's what you got here. Now, how can you convert this integral to something in terms of cos and sine? Let's think about it. What is secant? Secant is reciprocal of cos. So if we write secant in the numerator, this could be written in terms of cos, right? So we have 1 minus tan square theta multiplied by cos square theta. Now tan can also be converted to sine and cos. Tan is sine square theta over cos square theta. We have converted everything to sine and cos now. All right. So instead of tan, I've written sine over cos. Instead of secant square, I've just taken secant square to the numerator. What's the reciprocal of secant? It's cos. So when it goes to the numerator, it becomes cos square theta. And now everything is in terms of sine and cos. We just need to simplify this a bit and possibly get to one of these three forms. Let's try that. If we multiply cos square theta inside, what do we end up with? 1 into cos square theta, that's this cos square theta. And then you have sine square theta over cos square theta, cos square and cos square get cancelled, and we're left with sine square theta. And this is what we know from this first identity, that this is the same as cos of 2 theta. So we could write this as integral of cos 2 theta. And that's what we wanted to do in the first part. So we have replaced x with theta, and that integral converts to something much simpler now. In terms of cos, you have cos of 2 theta with respect to theta. Does this make sense? That's the first part. Okay. So you've done the substitution, converted everything from x to theta. Now let's look at the second part. Now in the second part, it says, hence find the value of this integral. Now it's the same integral as before, but now they've given us some limits as well. Yes?
So couldn't the cos square theta be cancelled with each other?
Okay, I'm sorry. Just give me a couple of seconds. Okay, could you repeat what you said?
So couldn't the cos square theta be cancelled with each other?
Where exactly?
Okay.
In this?
Okay, fine.
Yeah, we have brackets here, so it's multiplying with the whole thing.
Okay, sir.
All right.
Okay, let's look at the second part now. Now it says, hence find the value of this integral, and now you've got limits from 0 to 1. And now you have to input limits as well, okay? So what's that integral now? It's the same integral, but now it's with limits, and limits are from 0 to 1. Okay, limits are from 0 to 1. Now remember, the limits here are supposed to be values of x. Once we convert it to integral of cos of 2 theta, the variable that we've got here is theta now. So these x values also need to be converted to corresponding theta values. Now, this is something that you always have to do when you use substitution and you have an integration with limits. You have to convert the limits as well. You have to change the limits as well. So in this case, how would you change the limits? You would write down the upper limit and the lower limit on the side like this. You'll say this is the upper limit, this is the lower limit. For x, upper limit for x is 1, the lower limit for x is 0. Now it's necessary to write it separately like this, and you will understand that in the next 10-15 minutes why it's important to write them separately, write them very clearly. What is the upper limit, what's the lower limit? Because sometimes limits get interchanged in a way that the smaller value comes on top and the larger value comes at the bottom. The larger value becomes the lower limit. You'll end up making errors if you don't write it separately like this. You'll understand that from another example that we do after this. But write them separately. Write the upper limit separately, write the lower limit separately. X is supposed to be 1, that's the upper limit. The lower limit is x equal to 0. Now, what was the substitution that we used? X equals tan theta. So that means, in the case of upper limit, we have 1 equal tan theta, right? X equals tan theta. In this case, x is 1, so we have 1 equals tan theta. When is tan theta equal to 1? You take the smallest possible value in radians. Smallest positive value in radians. Tan inverse of 1. What's that? Just do that on a calculator, and that's going to give you tan inverse of 1 is pi over 4. In radians, it's going to be pi over 4. Similarly, if x is 0, you get 0 equals tan of theta. Tan inverse of 0, that's going to be 0. So the limits that you have in terms of theta now, they are from 0 to pi over 4. Limits for theta are from 0 to pi over 4. All right. So instead of 0 and 1 now, you got 0 and pi over 4 now. So you have to convert the limits as well when you do substitution and you have an integral with limits like this. Okay. This change of limits is important. Now you just integrate it like you would normally do. What's the integral of cos of 2 theta? Integration of cos is sine, so it becomes sine of 2 theta divided by 2. Limits are from 0 to pi over 4. You could write this 2 outside if you wanted, or leave it inside, that's your choice. If I take it outside, inside I'm just left with sine of 2 theta. Let's input those limits. Sine of 2 pi over 4 minus sine of 2 times 0. Okay, now sine of 2 pi over 2, that means 2 pi over 4, that means sine of pi over 2. What's sine of pi over 2? Sine of pi over 2 is 1. Sine of 0 is just 0. And we end up with 1 over 2. That's the result that we get from this integral. Integration of this expression with limits from 0 to 1, that is equal to 1 over 2. You can do that using substitution like this. And the limits for a substitution also have to change like we did here. Does that make sense? Any problem with this? Is this changing limits part clear to everyone? All right, good. Now let's have a look at one more example. Let me actually take it from somewhere. Integration, substitution. Yeah. This is from this paper, March 17. Let's have a look at this. Now, there's another small detail in this question that we want to understand using this example. There's another small detail in substitution that we want to understand using this example. Let's have a look at this now. We have this integral t equals integral of 10 over 5 minus square root of h with limit 0 to 4. We need to use the substitution u equals 5 minus square root of h and use that to find the value of t. Okay, now what's the integral that we're given? The integral is t equals integral of 10 over 5 minus square root of h dh. Limits are from 0 to 4. Now, what's the substitution that we've got to use? U equals 5 minus square root of h. Now, the first thing we've got to do is we have to differentiate this function. 5 minus square root of h, that basically means it's 5 minus h raised to the power 1 over 2. Now, what's du over dh? Derivative of u with respect to h. Derivative of 5 is 0. derivative of h raised to the power 1 over 2, that's 1 over 2 into h raised to the power minus 1 over 2. You've just applied the power rule here. Multiply by the power, subtract 1 from the power, right? And now you want to get rid of this dh as well. So you need to make dh the subject. If you make dh the subject, what does that give you? Okay, let me actually write it like this first. I could say this is dh goes to the other side. If dh goes to the other side, that gives me dh equal to, this 2 goes to this side. So we have minus 2 into du, and this h goes to the other side as well in the denominator. That's h raised to the power minus 1 over 2. And that gives us dh equal to minus 2. This is negative power of h. We could take that to the numerator if we want. So that becomes 2 minus 2h raised to the power of 1 over 2 du. This is one substitution that we had to put there. And dh will need to be replaced with minus 2h raised to the power of 1 over 2 times du. These are two things that we input in this integral. Let's try that and see what happens. What do we end up with? Now, leave the limits for now. We'll talk about that in a moment. Let's just convert this integral first. We have 10 over u. And then instead of dh, we have to write minus 2h raised to the power 1 over 2 into du. So we've put that substitution here, and we've also converted dh to du. However, the problem is we still have an h here. We still have this h here, right? What do we do with this h? We can make h raised to the power 1 over 2 the subject from this substitution and replace this h raised to the power 1 over 2 with u as well. How will that work? If we make h raised to the power 1 over 2 the subject here, that's going to give us 5 minus u. So this could now be written as integral of 10 into, in fact, I could just multiply this minus 2 outside to make things simpler. That's minus 20. And then what's h raised to the power 1 over 2? H raised to the power 1 over 2 is 5 minus u. In the denominator, I've got u and du here like this. This is the integral that we've got now. Make sense? Now everything is converted to u at this point. Now we also need to change the limits. How do we change the limits now? Let's write down the limits here on the side. We need to write what the upper limit is. And we need to write what the lower limit is. What's the upper limit? The upper limit is h equal to 4. Remember, these limits are supposed to be values of h because the original integral was in terms of h, right? So h equals 4. What's the corresponding value for u? That will be u equals 5 minus 4 raised to the power 1 over 2. That becomes 5 minus 2, which is 3. The value of u turns out to be 3. The lower limit for h was 0. So we say h equals 0. That gives us u equal to 5 minus 0 power 1 over 2. And the value of u turns out to be 5. Now, when we convert the limits, what we are getting is that the upper limit is 3 and the lower limit is 5. Now, that's very important. Don't just write the bigger number as the upper limit and the smaller number as the lower limit. The larger value of h corresponds to the smaller value of u, and the smaller value of h corresponds to the larger value of u. Now, the lower limit, therefore, is supposed to be 5, and the upper limit is supposed to be 3 in this case. Is that okay? Now, the upper limit in this case is smaller, and the lower limit is bigger like this. Okay. Now, you could either just evaluate it like this, integrate it, input 3 as the upper limit and 5 as the lower limit, and that's perfectly acceptable. You can do that. All right. You can just integrate it like this. Just make sure in case of upper limit, you put 3. In case of lower limit, you put 5. But this is not a standard way. This is not a conventional way of writing limits. Generally, we prefer writing the larger value as the upper limit and the smaller value as the lower limit. So we could actually change these limits. We could actually interchange these limits as well. And the way to do that is, if you want to interchange these limits, you can just multiply this integral with negative sign and change the limits. So if you wanted to write it the other way around, with 3 at the bottom and 5 on top, this would become 20 into 5 minus u divided by u du. So this minus sign gets eliminated. If you multiply the integral with -1, the limits can be interchanged. The upper limit and the lower limit, they can be switched like this. Okay. And now you just integrate it like you would normally do, input the limits, and you get the result. Okay. Now, how do you integrate this thing? We will think about this in a moment. In fact, I'll just write it down in the notes there as well. In substitution, this is something that you have to do sometimes. You have to switch the limits. So remember the rule that we've got for this. Whenever you have an
integrate with limits with 3 above and 5 below.
You can do it. You can do it. But I'll tell you a case where you have to switch the limits. Just give me a minute. Let me just write it down first. So if you have limits like this, they have b as the lower limit, a is the upper limit, and you want to integrate something like this, x minus y. Let me actually change the variables. Let's say you have p minus q. You want to integrate this with respect to x. If you want to interchange the limits and write it like this instead, that a becomes the lower limit, b becomes the upper limit, well, all you have to do is multiply this by a negative sign. Okay? Have a negative sign there, multiply the function by negative, and then you can switch the limits like this. Right? Because the thing is, you basically subtract the upper limit case from the lower limit, subtract the lower limit case from the upper limit case, right? If you have to switch the limits, if you put the negative sign outside, it becomes lower minus upper, right? So basically when switching, we can just put a negative sign here like this. Now, why is it necessary? Why can't we just do it like this? Do it as it was? That's what your question is, right? Why can't we just input these limits as they are? You can do that. That's possible. However, sometimes what happens is they might have told you in the question to convert this integral to a form like this, with 3 and 5 as the limits, and let's say they wanted the integral to look like this, 20 into 5 minus u divided by u with respect to u. So sometimes they ask you to convert an integral to a particular form. So they might ask you to convert this integral to this form, in which 3 is the lower limit and 5 is the upper limit. Once you get to this form, this step, then you should know how to go from this step to this. If you want to interchange the limits, if you want to switch the limits, you would multiply the function by a negative sign, and then you can switch the limits. So when you have to prove something like this, when you have to show something like this, in that case, it's necessary to switch the limits. Otherwise, you could do it without it as well. If you just had to evaluate the result, then you could do it without that as well, and that's also perfectly acceptable. But if you had to show it, then you would have to switch the limits. Does that make sense?
Yes, sir.
Okay. Now let's evaluate this integral. How would you integrate this now? We could write 20 outside if we wanted. Inside, we're left with 5 minus u over u. How can we integrate this? What method can we use?
So we can simplify first.
Simplify? What do you mean by simplify? Multiply 20 inside? Is that what you're saying?
Separate the numerators.
We can split the numerators. So think of the rules that we have for fractions. Does the ln rule work here? It doesn't. Tan inverse does not, because It's not tan inverse form, right? Log form doesn't work because numerator cannot be the derivative of denominator here. You can't do partial fractions. You can actually do quotient plus remainder over divisor as well, because it's also an improper fraction. But a quicker way of doing this would be just to split the numerator, right? That was one method that we discussed. If we just split the numerator, we could write this integral like this. We could say it's 5 over u. We could write it separately. Minus u over u, right? So we could split it into two fractions like this. Now the second fraction, that just becomes 1. And now we can integrate it. The first one is just 5 over u with respect to u. And the second one is integral of 1 with respect to u. Now, just remember, 20 is being multiplied with this whole thing. And now you just integrate it. Now I have written too many steps here. You could skip a couple of these steps as well, and that's perfectly okay. 20 into 5 over u. What's the integral of that? We could write 5 outside, and then integration of 1 over u is ln u. So it becomes 5 ln u minus integration of 1. What's the integration of 1? What's the integral of 1? What should be the integration of 1? Should it be x? Integration of 1 with respect to x is x. Here we are integrating with respect to u. So integral of 1 with respect to u would be u in this case. Okay? So this becomes u. And now we can input those limits from 3 to 5 and see what that gives us. That's 20 into 5 ln 5 minus 5. Subtract from that 5 ln 3 minus 3. We have 20 outside as it is. And inside we've got 5 ln 5 minus 5 minus 5 ln 3 plus 3. Now remember, we have to write down our answer as a single ln term. If we have multiple ln terms, we have to write it as a single ln term. That's necessary. Okay. So how can you do that? 5 ln 5 and 5 ln 3. We could take 5 common from these as well. You can actually just multiply this inside first. I'm going to have to do some simplification. So this becomes 5 ln 5 minus 2 minus 5 ln 3. If we multiply 20 inside, that gives us 20 into 5. That's 100 ln 5 minus 100 ln 3 minus 40. Now you can take 100 common. That leaves you with ln 5 minus ln 3 minus 40. And then it becomes 100 into ln of 5 over 3. It has to be written as a single ln term. And the final result turns out to be 100 ln of 5 over 3 minus 40. That's the final result that you get. You could write this in decimals as well in this case. Yeah, you could, because the question does not specify that you have to write down an exact answer. But generally, they prefer having exact answers. So this is how you would write it. If they wanted an exact answer, it's necessary to write your final answer as a single ln term. You can't have multiple ln terms. We talked about this before. There's generally 1 mark at the end to convert it to a single ln term. All right. Any problems with this? Any questions, anyone? So this is how substitution works. All right. This is all that we need to know about substitution, the process of substitution, and also about how to change the limits. You have to remember that limits sometimes are like this, that the smaller value ends up being the upper limit and the larger value ends up being the lower limit. If you want to switch them, you need to understand that process as well. Okay, so now we understand how to integrate by substitution. Now, the last thing that we have in this topic is how to integrate powers of sine and cos. Okay, how to integrate powers of sine and cos. That's the last thing that we want to do today. So let's have a look at that. Integrating powers of sine and cos. Let's talk about that. And then we're done with all the concepts that we need to know about. So first of all, so there are two types of powers that you could have. You could have odd powers and you could have even powers. In odd powers, you would only have 3 generally. Okay. You want to be able to integrate odd powers of sine, cos, and tan. Okay. So power 3 of sine, cos, and tan. Now, all of these are basically done using substitution. So sine cube, cos cube, and tan cube, they are all integrated using substitution. Okay, they're all done using substitution. Now, since they will always tell you what substitution to use, so it's not that difficult, but you still need to remember how to actually use that substitution. So let's understand that process. So first of all, you need to be able to integrate this function sine cube x with respect to x. Okay, this is one function that you will need to integrate using substitution. Now for this, they will give you the substitution u equals cos of x. This is the substitution that they will give you in the question, that you have to use this substitution. U equals cos x. Okay. Now, how do we use u equals cos x for integrating sine cube x? We don't even have cos x here. What do?
We differentiate u and we'll get sine.
Okay, so that, yes, so that's one thing that we have to do. Okay, let's do that. Let's differentiate it. Du over dx. Derivative of cos is minus sine, so it becomes minus sine x. Now you have to eliminate dx as well. So dx is equal to minus du over sine x. Okay, that part is fine. We can replace dx with du over sine x. What about u equals cos x? Where will we put this? U equals cos x. What we can do is we can actually break this power 3 into 2 parts. We can break it like this. We can say sine cube x is the same thing as sine square x into sine x with respect to x, right? That's what it is. Sine cube x could be broken down into 2 parts like this. And once you break it down into 2 parts, now what is sine square x? Sine square x can be written as 1 minus cos square x. And now you could use that substitution here, because now you've got a cos x term as well. You would replace cos x with u and dx with minus du over sine x. Now you can put both of those substitutions here and see what happens when you do that. It becomes integral of 1 minus u squared into sine of x into dx. Dx is minus du over sine x. Now sine x and sine x get cancelled, and we are left with integral of minus 1 minus u squared du. Now you could multiply the negative sign inside. That leaves you with integral of u squared minus 1 with respect to u. Now this is something that you can integrate quite easily using the power rule. What's the integration of u squared? Integration of u squared is u cube over 3. Integration of 1 is going to be u. Now you put that substitution back. What was u equal to? U was cos of x. So you say the integral at the end turns out to be cos cube x divided by 3 minus cos of x plus c. That is your final result. Now, if you had some limits here instead, you could just convert, you could just change the limits to u as well, and this just input limits here. But in this case, you were supposed to find the function, find the integral at the end in terms of x. So that's why you have to put that substitution back. In place of u, you put cos x here again. So this is how sine cube x is integrated. They will give you a substitution in this case. Okay, they will give you what substitution to use. Let's take another example. The second function here is cos cube x. So they will also want you to integrate cos cube x. In this case, the substitution they're going to give is u equals sine x. Now, exactly the same process works here. So I'll do it very quickly. Now, again, the substitution that you want to use is u equals sine x. So you split it into two parts like this. In this case, you say this is cos square x into cos x with respect to x. Differentiate it, du over dx. What's the derivative of sine x? It's cos x. Now you make dx the subject. That leaves you with du over cos x. In this integral, cos square x can now be written as 1 minus sine square x into cos x dx. Put that substitution here. Instead of sine x, you put u, so it becomes integral of 1 minus u squared into cos x into du over cos x. Now cos x and cos x get cancelled, and we're just left with integral of 1 minus u squared with respect to u. This you can integrate directly. Now, what's the integration of 1? Integration of 1 is u. Integration of u squared is u cube over 3. And now you can put that substitution back. U was supposed to be sine x. So it becomes sine x minus sine cube x divided by 3 plus c. That's the result that we get from this. Okay, so it's almost exactly the same process. There is nothing different, right? Make sense? That's how cos cube x is integrated. So we learned how to integrate sine cube. We learned how to integrate cos cube. Now, finally, we have tan cube. I'll just take, it's just going to take 20, 25 more minutes now, I think. And then we end. Okay, so it'll take like 25 more minutes. We also need to do even powers. So it's going to take at least 20 more minutes, maybe 25, something around that time. Okay. All right. Now, what about tan cube? How do you integrate tan cube of x with respect to x? Now, tan cube can be integrated using this substitution. Again, they will tell you what substitution to use. So they'll tell you, in this case, u equals tan x. This is the substitution that you've got to use. Okay, u equals tan x. Now, in this case, we already have tan x here. So if we just put this substitution there directly, right, we can do that. So this becomes integral of u cubed then. What about dx? We have to find the derivative of that. Du over dx. What's that? That's secant square x. Derivative of tan is secant square. Now you make dx the subject. And that gives you du over secant square x. So you have u cubed into du over secant square x when you do that substitution. This is what you end up getting. Now the problem is we still have an x here. How do you get rid of this x? How can we get rid of this x?
By using the other equation, u is equal to tan x.
How do you do that? This is secant square. This is tan x.
First, it will become 1 over cos square x.
How does that help? We want tan x. Remember the identity.
Sin x over cos x.
Again, where will sine come from? Remember the identity. You could actually do it, but that's going to take quite long. You could connect secant square and tan square directly. Remember that identity? We used that earlier today as well. 1 plus tan square is secant square x. So in the denominator, we could write this as 1 plus tan square x. All right. And now we could convert this tan to u. So what do you end up with? You end up with an integral like this, u cubed divided by 1 plus u squared with respect to u. So now everything is converted to u. The substitution process is done. How do we integrate this now? U cubed over 1 plus u squared. What method do we have to use? ln rule does not work. Tan inverse doesn't work. Partial fractions don't work. Is it tan inverse form, by the way? Is it tan inverse form? Can this be integrated to tan inverse? For tan inverse, in the numerator, you want a constant. Denominator is that form, yes, 1 plus variable squared, but in the numerator, you want a constant. It's not a constant, so tan inverse does not work. What do we do now? What options do we have?
Sir, we didn't substitute.
We have converted everything to u now. Everything is converted. Nothing is left.
Oh, okay.
How do we integrate this? U cubed over 1 plus u squared.
Sir, partial fractions?
Partial fractions need factors in the denominator. We don't have any factors here. Remember improper fractions? How did we use to integrate improper fractions? Division, right? This is an improper fraction. Degree of the numerator is greater than the degree of the denominator. You'll have to divide it into quotient and remainder over divisor. How do you do that? Using long division. U cubed divided by u squared plus 1, you can say that's u squared plus 0u plus 1. U squared into u is going to give you u cubed. So you have u here. That gives you u cubed plus 0u squared plus u. Change the signs. This becomes minus, minus, minus. This gets cancelled. And you have minus 0u squared minus u. What do you multiply? In fact, 0 is just eliminated basically. And you have minus u now. What do you multiply u squared by to get minus u? You can't do that anymore. That's the final result. This is the remainder. This is your remainder. And this is the quotient. Remember that rule? Dividend over divisor, that's quotient plus remainder over divisor. So we could split it into two parts like this. Quotient, which is u, plus remainder, which is minus u. So we could say minus u over divisor, which is 1 plus u squared. We could convert it into two fractions like this, or two parts like this, right? Quotient plus remainder over divisor. We have discussed this before. That's how we integrate improper fractions. And now we just integrate both of these separately, integrate u separately with respect to u, and integrate u over 1 plus u squared separately with respect to u. U can be integrated using the power rule. That's just u squared over 2. What about this? This is a fraction. We could use ln rule here. The derivative of u squared plus 1 is 2 times u. You want 2u in the numerator, right? So you can multiply by 2 inside, and to balance that, divide by 2 outside, and it becomes 1 over 2 into ln of 1 plus u squared using the ln rule. And now you put that substitution back. U was supposed to be tan x. We have done the integration, put that substitution back now. Tan square x divided by 2 minus 1 over 2 into ln of 1 plus tan square x plus c, that is the integration of tan cube x. This is how we integrate tan cube x using substitution. Is that okay?
Yes.
All right. So sine cube, cos cube, and tan cube, they are integrated using substitution. They will always give you what substitution to use. All right, good. Now, the last thing that we want to do now is integrating even powers of sine, cos, and tan. Integrating even powers of sine, cos, and tan. In particular, we want to focus on powers 2 and power 4. This is done using trigonometric identities. So substitution part is done. Now, this is another type of integration that you need to know how to do. They will not give you hints about it generally. You'll have to figure it out yourself. So you need to remember this. You need to remember how you're going to integrate sine square, cos square, tan square, and sine raised to power 4, cos raised to power 4, right? You need to be able to integrate all of these. Now, how are even powers integrated? You need to remember even powers of these trigonometric functions are integrated using trig identities. Okay. Now let's see how that is going to work. Let's start with sine square x first of all. So the idea is this is sine square x, right? Remember, we cannot use power rule here. So this function is sine of x whole squared. We can't say that use power rule like this, sine x raised to power 3 divided by 3 and then divide by the derivative of sine, which is cos x. It does not work like this. Power rule only works for linear basis. When inside the power, you've got something linear. Now, linear means mx plus c form, right? Straight line form. It's not just that the power of x should be 1. So here in sine x, power of x is 1, so it's linear. It's not like that. Sine x is not a linear function. That's a curve like this. Power rule does not work on that. Okay, so we cannot integrate it using power rule. So we need to somehow get rid of the power here because power is going to make it difficult to integrate. So we don't want sine square here. We want the power to be just 1. Okay. Now look at the formula sheet and think about what different identities you have for sine square. Sine square comes in 2 identities in the formula sheet. One is sine square plus cos square identical to 1. If you were to use that, you could write sine square as 1 minus cos square, but that's not really very helpful because you still have a square. How do you integrate cos square then? So it's not going to help. There's another identity where you have sine square in the formula sheet in trigonometric identities, and that is the double angle identity for cos. There are 3 different forms for that. The form in which you have sine square that looks like this, cos 2a equals 1 minus 2 sine square a. You will use this identity to get rid of the power. How do you do that? If you make sine square the subject here, what does that give you? Sine square a, that's identical to, so let me write it like this first, 2 sine square a, that's identical to 1 minus cos of 2a. Then just divide this 2 on the other side, and it becomes sine square a equals 1 minus cos 2a divided by 2. So you can use this identity to convert sine square x to 1 minus cos of 2x divided by 2. And now you've gotten rid of the power. This is something that you can integrate. You can write 2 outside if you want. If you write 2 outside, it becomes this 1 over 2 outside. Inside, you're left with 1 minus cos of 2x integration of that. Now, what's the integration of 1 minus cos of 2x? What's the integral of 1 with respect to x? 1 with respect to x, that will be x. Integration of cos 2x, cos integrates to sine and becomes sine 2x over 2. And the final result turns out to be 1 over 2x minus 1 over 4 into sine of 2x plus c. So sine square x is integrated using the double angle identity of cos like this. You need to remember this. They will not give you a hint about this. You need to remember that sine square is integrated using this method. Okay? That's the integration of sine square. Now, what about cos square? That looks very similar. Integration of cos square. Let's actually use theta this time instead of x. So what about integration of cos square theta? Again, which identities does cos square theta come in? You have sine square theta plus cos square theta identical to 1. That's not helpful because, again, it would still be a square. There's another identity, and that's, again, the same double angle identity for cos, in which you have cos square as well. You could use that. Cos 2a is also 2 cos square a minus 1. If you make cos square a the subject in this case, that gives you 1 plus cos of 2a whole divided by 2. And you could replace cos square theta with this now. You would say this is 1 plus cos of 2 theta divided by 2 with respect to theta. Okay, and then similarly to what we did above, you could write 1 over 2 outside. Inside, we're left with 1 plus cos of 2 theta with respect to theta. 1 over 2 outside remains as it is. What's the integral of 1? What's the integration of 1? Quickly. What's the integration of 1?
Theta.
Theta. Don't write x here. This is theta because we are integrating with respect to theta. Integration of 1 with respect to theta is theta. Okay, so it becomes theta plus integration of cos 2 theta. What's that? That's sine of 2 theta divided by 2. That's the integration. Now you could simplify this. 1 over 2 theta plus 1 over 4 into sine of 2 theta plus c. That is how you integrate cos square theta. So both sine square and cos square, they're integrated using the double angle identity for cos. Again, you will not get a hint for this in the exam. You will need to remember this, that this is the identity that you have to use for this. Okay. Let's take another example. What about tan square now? Integration of tan square. Now, again, look at the formula sheet and think about where does tan square come in the formula sheet? What identity can make it simpler, maybe? Can you find anything in the formula sheet? Trigonometric formula sheet. Let me just open that for you. Tan square. Where is tan square? Okay, tan square is here. And it's in the double angle identity of tan as well. Now, this is going to become very complicated because when you make tan square a the subject here, it will be a fraction, a complicated fraction. You have this as well. Do you think this could help?
Yes, sir, because we could later convert secant into 1 over cos, and we could convert cos as usual with double angle identities of cos.
No, but cos will be in the denominator in that case. Let me actually show that. So let's use that identity and see what that gives us. 1 plus tan square a. The formula sheet says that is equal to secant square a. So tan square a, what does that equal? That equals secant square a minus 1. Let's use this identity and see what happens. So this could be written as secant square x minus 1. Now you're telling me I could write secant square as 1 over cos square. Okay. What do we do after that? If you use this identity, you would have 2 over 1 plus cos of 2x. What do you do after that? There isn't much that you can do with this. Can you think of something else? Don't you know the integration of secant square directly? Integration of secant square is tan. It's written in the formula sheet. The derivative of tan is secant square. Integration of secant square is tan. So secant square just integrates to tan. So this becomes tan of x. Integration of 1 is x. So we have tan x minus x plus c. That's the integration of tan square x. Okay. So this is how we integrate sine squared, cos squared, and tan squared. Okay.
Yes, sir.
Now we have power 4. That's the more complicated part. Let's just do that and then we end for today. Sine raised to power 4. How do you integrate this? Sine raised to power 4, or sine raised to power 4x with respect to x. We want to integrate this thing with respect to x now. Sine raised to power 4. Now we could write this as sine square x whole squared, right? And use the double angle identity again, just like we used that for sine square. We can do exactly the same thing. But this process is going to be slightly longer than before, because then you'll have to convert square back to power 1 as well. Let's try this. Remember the identity that we have for cos. So leave it here as it is. Let's first figure out how sine raised to power 4 can be converted to another form that's easier to integrate. Again, let's use that same identity. Cos of 2a, that is 1 minus 2 sine square a. Okay, or we could write it in this form in place of, in terms of x. We could say cos 2x is 1 minus 2 sine square x. Okay, now from this, what we can do is we can make sine square x the subject. If we make sine square x the subject, that's going to give us 1 minus cos of 2x divided by 2. Sine square x equals this thing. But what we want is sine raised to power 4x. So how do we get that? We can just take square on both sides. On the left side, we have sine power x. On the right side, we get 1 minus cos of 2x over 2 whole squared. Okay, so sine raised to power 4x could be written like this. But this is still something that cannot be integrated directly, right? Because we have a whole power and the expression inside is non-linear. So we can't use power rule. It still needs to be simplified further. Let's simplify this further and see what that gives us. In the denominator, we have 4, right? 2 squared is just 4. What about the numerator? In the numerator, we have a minus b whole squared. That's going to be a squared minus 2ab plus b squared. That becomes 1 minus 2 cos 2x plus cos squared 2x. Okay, that's what we get. 1 minus cos of 2x, 1 minus 2 cos 2x plus cos squared 2x. Can we integrate this expression now? 1 can be integrated. 2 cos 2x can be integrated, but we still have a problem. What about cos squared 2x? We still have a square here. We also need to get rid of this square. Okay? In order to be able to integrate this whole expression, we also need to get rid of this cos squared 2x. Now, how do you do that? I can write this 4 outside just to make things a bit simpler. Inside, I have 1 minus 2 cos of 2x. Now, what about cos square of 2x? Again, let's use that identity. Cos of 2a, what was that equal to? Cos of 2a was 2 cos square a minus 1, right? Let's make cos square a the subject, and that gives you 1 plus cos of 2a divided by 2. Now, instead of cos square a, you have cos square 2x, 2 times something. Now, look at this identity. If on the left side you have a, on the right side you have 2 times a. If on the left side you had 2 times x, like you have here, the angle on the right side, that should be 2 times that, because a multiplied by 2, that gives you 2a. 2x multiplied by 2, what should that give you? That should give you 4x. So you have 1 plus cos of 4x divided by 2. So now cos square 2x, this could be written as 1 plus cos of 4x divided by 2. And now you have all the powers eliminated. Now you've got all the powers eliminated. Now this is something that we can integrate. Now let's simplify this a bit first. We could write it as 1 over 4 minus 2 over 4. That's going to be 1 over 2 into cos of 2x plus 1 over 2 into 1 over 4. That's going to be 1 over 8 plus cos 4x over 2 into 1 over 4. That's going to be 1 over 8 into cos of 4x. This is what we can write sine raised to power 4x as. So sine raised to power 4x, that can be converted to this form. So basically it's more trigonometry than integration, because the main thing was to convert that whole thing to this form. Generally, it comes as a 2-part question as well, in which the first part they would ask you to convert this to this form, and then in the second part they might ask you to integrate this. But even if it comes in one part, this is how you would have to approach it. Apply the double angle identity for cos twice in this case. Once you would reduce power 4 to power 2, and then you apply that again to reduce power 2 to power 1. You'll have to apply the double angle identity twice in problems like these. Okay. So now that we know sine raised to power 4x can be written like this, we can say integral of sine raised to power 4x with respect to x, therefore, that can be integral of 1 over 4 plus 1 over 8. By the way, what's this? 1 over 4 plus 1 over 8?
8.
3 over 8?
Yes,
So
sir.
this becomes 3 over 8 minus 1 over 2 cos 2x plus 1 over 8 cos of 4x. And now we can integrate this whole thing. We can integrate each term separately. What's the integration of 3 over 8? That's 3 over 8 times x. Integration of 1 over 2 into cos of 2x. 1 over 2 remains as it is. Integration of cos is sine. So that becomes sine of 2x divided by 2, the derivative of 2x, plus 1 over 8 remains as it is. Integration of cos is sine again. So it becomes sine of 4x divided by 4. And that simplifies to 3 over 8 times x minus 1 over 4 into sine of 2x plus 1 over 32 into sine of 4x plus c. This is the integration of sine raised to power 4x. So you apply that double angle identity twice like that. Okay. Make sense to everyone?
Yes.
Okay, now what about cos raised to power 4x? That's almost exactly the same process. So I'll leave that as an exercise for you. I'll just show you the solution directly here because it's almost exactly the same thing. It's just the plus minus that are different. So if you had to integrate cos raised to power 4x, how would you do that? I'm just going to copy this whole thing and just make some changes to it, and you would realize what that means. So if you had cos raised to power 4x, what about the integration of this now? Again, you use the double angle identity for cos. You're going to start like this. Cos 2x, use the other form now. The other form is 2 cos square x minus 1. Use this form. Okay. When you use this form, you'll have cos square x the subject. When you make cos square x the subject, that's going to be 1 plus cos 2x over 2. Right? And then what about cos raised to power 4x? That's going to be 1 plus cos 2x over 2 whole squared. Right? This is what we get. Now we could simplify this. Now you see, the only difference from above is we had 1 minus cos 2x here. Now we have 1 plus cos 2x over 2 whole squared, right? So it's pretty much the same process after this. Now 1 plus cos 2x whole squared, what does that evaluate to? 1 plus 2 cos 2x plus cos squared 2x divided by 4. Then in the next step, it becomes 1 plus 2 cos 2x, and then cos squared 2x could be written like same thing using that identity. And now when we write it separately like this, it becomes 1 over 4 plus 1 over 2 cos 2x plus 1 over 8 and plus this. And you integrate it, it becomes 3 over 8 plus 1 over 2 cos 2x plus 1 over 8 cos 4x. And you have plus here as well. And you have plus here as well. And that's the integration of cos raised to power 4x. So there's just one term that changes sign. Everything else remains exactly the same. It's the same process exactly. Okay, so that's the integration of cos raised to power 4x. So this is how we integrate powers of sine and cos. If you have odd powers, they will give you a substitution. If you have even powers, you can use trigonometric identities. Okay. And that completes integration for us. What different methods have we done? Now, the most tricky part in integration is generally figuring out what formula, what rule to use to integrate a particular function. So this is how you can actually think about it. There are 3 possibilities that would generally be there. One possibility would be that you have a simple function that can be integrated directly, which means you have one of these functions. One of these functions that can be integrated directly. You know the rules for them directly. That is one possibility. If you have a function like this, you just integrate it directly, okay, using these rules. Then you could have a product. If you have a product, you have 2 possibilities, only 2 possibilities. You could use substitution or integration by parts. So if it's not one of the earlier forms where you can use direct formulas, for example, for secant x into tan x, you could use this direct formula that this integrates to secant x. But if it's a product other than that, for which you do not have a direct rule, you only have 2 possibilities. You can either use substitution or you can use integration by parts. If it is substitution, they will always tell you in the question that you have to use substitution. If they don't tell you and it's a product, what do? You use integration by parts. Okay. Then you have fraction. In fraction as well, you could use substitution if it's given. If you have to use substitution, they will always tell you about that. Okay. If it's not substitution, then you have to think of all of these other rules that we have done. The ln rule, where numerator is the derivative of the denominator, tan inverse rule, partial fraction, and then using ln and tan inverse rule afterwards. These two other forms of partial fractions that are given in the formula sheet directly, where you have constant in the numerator and x squared over x squared minus a squared, or a squared minus x squared in the denominator. Or you could split the numerator like this into two parts. If you have an improper fraction, in that case, you use this rule. Dividend over divisor is quotient plus remainder over divisor. So in fractions, you have to think of all of these different rules. And if none of them works, the last resort generally is to take the denominator to the numerator. So for example, if you had 4 over 2x plus 1 whole raised to power 5, you could take the denominator to the numerator. In this case, it would become a simple power function that you can integrate using the power rule, because the part inside is linear. If you had something like this, for instance, ln x over under root x, none of the fraction rules work here. In this case as well, you could take the denominator to the numerator, make it a product, and use integration by parts in this. Sometimes you have to do this. None of the fraction rules works. In that case, you just take the denominator to the numerator like this. These are the rules for fractions. And then if you have odd powers of trigonometric functions, they will give you a substitution. If you have even powers, you have to use trigonometric identities. You need to remember that. And the most commonly used identity is the double angle identity for cos in this case. All right. Now, just another example before we end. How would you integrate this? One last thing. 4 over cos square x with respect to x. How do you integrate this? Any idea about this? 4 over cos square x. Does any of the rules that we have done, does that work here? It's a fraction. It does not follow the ln rule. Numerator is not the derivative of denominator. It's not tan inverse form. We can't do partial fractions. It's not an improper fraction. We can't split the numerator. None of those rules work. What can we do? If you had that, trigonometric identities are when you have cos square x, sine square x, tan square x in the numerator. This is in the denominator. So that double angle identity to reduce square to a single power is when you have these powers in the numerator. This is in the denominator. What's 4 over cos square? Cos is reciprocal of secant. We could write it as 4 secant square x. And secant square is something that we know the integration of directly. It becomes 4 tan x plus c. So sometimes you end up getting something slightly tricky like this that does not follow the rules, but you need to be able to think on that spot that, okay, 4 over cos square, cos is actually reciprocal of secant. So it could be written as 4 into secant square like this, and then integrated directly. All right. So that completes all of our integration concepts. In the next session, if you have attempted some questions, we will be looking at the problems that you have. We will be practicing questions from the worksheet or from any other recent papers. And then we start differential equations after that. All right. Now, those of you who are on YouTube, just a reminder, I have my past paper session starting on 13th of April. If anyone of you is interested, you can have a look at the description. The link for registration is there. You can find all the details about the course in that registration form. You have 2 days until the deadline for the early bird discount. That's until 5th of April. So that's like 1 day left now only. Yeah, 2 days. The discount ends on 5th of April. You can look at the registration form, the fee details for all the components. And you'll find answers to most of the questions that I've been getting from different students, the answers to frequently asked questions on my Instagram, like how many years of past papers will be covered, how many sessions we're going to have for each component. Will we be covering full-length papers or just the difficult questions? All of those questions are answered on my Instagram and also in a couple of YouTube posts. If you look at my channel, you can find that there as well. Most of the questions are related to the course, related to the past paper sessions are answered there. If you have any other questions apart from that and you want to register, you can leave me a message on WhatsApp or Instagram as well, and then I'll get back to you to basically answer any other queries that you have. All right. These lives are actually quite random. There's no specific time for this. In fact, we'll probably be ending these lives. So I was just doing these lives so I have a crash course session. This class is actually from a crash course that I'm doing right now. So we were doing P1 functions recently and P3 integration now in paper 3. So since these were the two relatively more difficult topics from each of the papers, I just wanted to make them public for everyone. But it's actually part of the crash course that has been ongoing since January this year. So it's actually part of that course. So these are just two specific topics that we were doing at this point in time. Since a lot of students have problems in these two topics, I just made these two public. Integration is now ended. I might be doing differential equations as well, live for differential equations as well. That will be now Friday, Saturday, and possibly Sunday. That will be around 4:45, 5 p.m. Pakistan time for P3 differential equations. That's all that I'll be doing, I think, in the next week or so. Where you can find all the content covered on my YouTube channel already as well, by the way. You have P3 playlist, you have P1 playlist, you have S1 playlist, M1 playlist, where all the syllabus content is covered. So you can have a look at that as well if you have any particular concepts that you want to touch upon. All right, but I have this past paper session starting, which in case you want to ask any questions, if you want to be part of these live sessions, participate in classes, ask me questions if you have any, you can join those past paper sessions in which we'll be covering a lot of the recent past papers from 2020 to 2024, the last 4 or 5 years of past papers, including March 2024. But that's for the past paper session only. Concepts we're mostly done with. That session is starting from 13th of April. If you want any more information about that, you have the link for that. You can have a look at that. All right, any questions, anyone? Any problems? Those of you in class right now. Is that it? Marina, you've been silent. How is it going for you? You missed quite a few classes as well. All right, good. So I'll see you again on Friday. On Friday, we'll be doing some practice questions on integration, and most likely on Saturday, we will be starting differential equations then. All right. Allah Hafiz, everyone. Bye. I'll see you again in the next class.
Allah Hafiz.